So it's my real honor and pleasure to introduce our colloquium speaker today, Professor Markus Greiner from Harvard. So, Markus has a truly remarkable sort of track record of doing trailblazing experiments in cold atom experiments, specifically related to kind of quantum simulation of condensed matter and solid state physics, starting with his PhD, which he did at LMU and MPQ in Munich. Markus was sort of really pioneered the first experiments that observed superfluid to Mott insulator transitions in BEC experiments in lattices, in 3D lattices, in bulk experiments. And then he went on at Gilla, which I should say, by the way, he won the Demop Thesis Prize for that work, which was the first of many awards, as you'll soon see. He then went on to do a postdoc at Gilla with Debbie Jin, where he did some of the early experiments in Fermi degenerate gases and observed BCS to BEC crossover in Fermi degenerate cold atom experiments. And then he went to Harvard to start his own group, where he made the very first quantum gas microscope experiments, moving from doing these kinds of quantum simulation of cold atom experiments where you only observe bulk properties to doing experiments where you can actually observe the single atoms as they experience this kind of exotic condensed matter and many-body phenomena. It's almost as if looking inside of a metal or conductor and being able to see the individual electrons. Really beautiful experiments. I was fortunate enough to be a young graduate student, maybe first or second year graduate student at Harvard when Markus and his group first got the quantum gas microscope working, and I remember all of the excitement that surrounded that. And I hope you'll forgive me for mentioning this, but I will always remember the Harvard Crimson, the Harvard newspaper, the student newspaper there. The headline was "Physicists Create Microscope," which somehow both sort of oversells and undersells the results at the same time, which is kind of an amazing accomplishment. And since then, that was now, it's hard to believe, but I don't know, more than 15 years ago. Let's not say how many more. And most of the experiments that have been done with these quantum gas microscopes, which have since proliferated around the globe, have been kind of proof of principle, beautiful experiments demonstrating really beautiful physics, but mostly physics that we already understood, kind of recreating physics that we see in condensed matter systems already, and that theorists kind of can predict. But now this is a really exciting time for the field, and an amazing time to have Markus here telling us about his results, because now for the first time, Markus and some of the other groups around the world are really starting to observe phenomena that I think we didn't predict, it's fair to say, maybe, and don't fully understand. And so this is really quantum simulation kind of delivering on the promise of teaching us new things about condensed matter systems and about the world. So it's really an exciting time. It's great to have Markus here. As I mentioned, he's starting with a Demop Thesis Prize, won too many awards for me to list all of them, but a handful of highlights would include the MacArthur Fellowship, or otherwise known as the Genius Grant, the II Robbie Prize. He's an APS fellow. He is a Vannevar Bush fellow. So anyway, it's an honor and a pleasure to have you here, and we're looking forward to hearing about your results.
Yeah, thank you. Thank you so much for the very kind introduction. So, but before I start, I should mention why I look so silly. So I'm still working on recovering from my last COVID 2 years ago, and have significant long COVID. I need to delay the next one as much as possible. And so this is a very convenient way to do that. Stay safe. People say it looks like a beekeeper. I would prefer it looks like an astronaut, maybe. So how about... anyway, good. Yeah, thank you so much, Simon. You kind of gave my first few slides already. So because I put together a little history of quantum simulation. I was actually asked to do that for a conference I attended last week, and so I thought I start out with that. So, of course, these ideas of doing quantum simulation go back to Feynman, who realized that if you try to compute quantum mechanical system, then the Hilbert space really grows exponentially, right? And so that is really hard until today to treat with a computer. And well, no wonder until today, because this is a fairly fundamental reason that capturing this entanglement is genuinely hard, right? If you have a spin chain, you want to simulate it exactly. For every spin you add, you double the size of the number of qubits you need. You double the size of the computer of the Hilbert space. And if you have a spin chain of only 200 spins or so, you would already need more bits than there are atoms in the whole universe. So, of course, often you can do kind of like clever tricks if it's if the state can be described semi-classical or so, but that's not always clear how to do it. It's not always clear a priori how you can set up a computation that is reliable and so on. And so the idea was to use one quantum system that is more accessible, more controllable, to emulate another one. Seth Lloyd then made these ideas a bit more concrete, kind of, and in the 90s, these two ideas also came out that you can either try to do a quantum simulation that is analog, meaning that you build a system that is analog to an actual system, like a one-to-one correspondence, right? Or you can even do it a bit more indirect. You can use things like Floquet engineering, and trautorization to emulate one quantum system that's a bit different than the system you have at hand. Or then, of course, the digital one also includes what picked up a lot of steam recently, namely, once you have an actually full-blown quantum computer, of course, you can also use that to efficiently study and explore many-body quantum systems that are relevant to things like condensed matter physics or so, right? And in general, strongly correlated quantum problems all over physics, right? Things started to get really exciting in the early 2000s when, as Shimon already said, we were able to realize a condensed matter Hamiltonian in the strongly correlated regime, meaning where it's not just where the atoms are not just weakly interacting, creating some kind of quasi-classical state. Instead, you really have a genuine, strongly correlated quantum state there. And the idea is that this was possible with atoms in optical lattices. So we have atoms at extremely cold temperatures moving in periodic potential landscapes that are formed of light, and they then form a direct model system to the kind of physics that you encounter if sorry for that, if electrons are moving in a real material, right? In the 2000s, then other platforms started to pop up. There was some interesting work with NMR, but that wasn't really scalable. But then also trapped ion system and superconducting qubit systems became a thing, and these ideas also transitioned from not only condensed matter also to chemistry. And then, of course, Debbie Jin made these amazing contributions, so where she started to work, so all of these systems I just showed you actually, like the ion traps and superconducting and our cold atoms in optical lattices, they all work with bosonic particles, bosonic degrees of freedom. But of course, if you want to do quantum simulation of condensed matter models, you better use fermions, because your electrons in materials like high temperature superconductors or topological materials and so on, they are fermions, of course, right? And so what Debbie did was to cool fermionic atoms down, and this then even led to the discovery of utilization of a continuous crossover between a Bose-Einstein concept of molecules all the way to a BCS-like superfluid state that is made up of Cooper pairs that are formed of pairs of atoms. So there's a continuous crossover BCS-BC between molecules and Cooper pairs of these atoms, and so that was really exciting to study. But then, so there were a lot of kind of like bulk systems to study the strongly correlated physics, but it wouldn't be nice if you could just stop time and do a full projective measurement, right? Like in condensed matter, imagine you could stop time and could take a snapshot of where every single electron is in your crystal, right? That could help you a lot to understand things like high temperature superconductivity or so, if you could just look and see what's going on, right? And so in the case of ultra-cold atoms and optical lattices, this became possible with quantum gas microscopy, where you can both take full projective measurements and also control things on the single particle level. But this also shows you, if you look at a picture like this and you see, so each spot here, each bright spot is exactly one atom that you find on a lattice side. The amazing thing is, before you take this picture, every of these atoms is everywhere. Every of these atoms is quantum mechanically delocalized over the whole lattice, because this is a Bose-Einstein condensate. So if you have a Bose-Einstein condensate and optical lattice, the quantum mechanical state you write as particle number 1 is everywhere, particle number 2 is everywhere, particle number 3 is everywhere. And as you scatter the first photons in this imaging process, this many-body wave function collapses and you find particles at particular locations. But before you took that picture, all of these atoms really were at all the places at once. That sounds kind of surprising, and that's even possible. But if you think about it, again, in every piece of material, the electrons are at many places at once, right? Or like in chemical orbitals, like a benzene ring or so, right? We just don't see it. But electrons are typically quantum mechanically delocalized in these materials, and the same we can then realize with the cold atoms. In the 2010s, of course, the Rydberg systems became a thing, and so, well, as you all know, there's a lot of exciting things there. You can do quantum analog simulation, or you can even try to build a full-blown quantum computer, and the same, of course, for these superconducting systems. And there's also some interesting work then with photonic simulators. But until today, most of the quantum simulation, as Shimon said, was really like realizing cool many-body states. Like you can imagine condensed matter theorists, for example, come up with an interesting many-body quantum state that doesn't really exist like this in nature. And so we can then use the quantum device to realize this in real life. And to me, that was always a lot of fun to go ahead and actually make a state that has a certain kind of entanglement, that has these superfluid properties, and so on and so on. But what is just now happening is that we really get into regimes where we can push these quantum simulations into an area where the computations are not reliable, where the computations are approximate numeric methods, and or things like dynamics we can't compute at all. But we can do experiments there, and now we can really start to address open questions in condensed matter physics. And so this is what the rest of my talk will be about. Here's the team who is doing the experiments, and the collaborating theory team for our first paper on this topic at the Flatiron Institute. So Yeah, so we are using, so one of the things that was missing in previous quantum simulations is that we weren't quite cold enough. That sounds a little funny because we are actually very cold, these experiments, right? These are, here you can see a magneto-optical trap. The first step is always to use laser cooling to slow atoms down to create a cold sample of ultra-cold atoms. But then there are additional cooling steps like evaporative cooling and so on. I will show you some tricks later in this talk how we were able to significantly lower those temperatures. We then load the cold temperatures, in this case fermionic atoms, into an optical lattice. And the beauty is that these ultra-cold atoms in the optical lattice in two spin states here, so red and blue corresponding to spin up, spin down. These atoms are a virtually perfect realization of a very famous Hubbard, of a very famous model in condensed matter physics, namely the Hubbard model. The Hubbard model consists of only two parts. It's simply describing how atoms tunnel from lattice side to lattice side and how they interact. So the atoms move from side to side via quantum mechanical tunneling. What does that mean? Let's look at this a bit more closely, because this is not like classical hopping around. As I said earlier, everything's delocalized a lot, right? Also, this picture up here is a snapshot, right? Before we take the picture, everything is everywhere. To illustrate this, let me show you a simple kind of a quantum walk motion of particles in the optical lattice. So here, this is a two-dimensional lattice, but we only, let's say we only turn on tunneling horizontally here, and we initialize it with a state where we have exactly one particle in each of these lattice sites. And if we then turn on horizontal tunneling, the wave function of this particle would spread out, like so. And then we can let the wave function evolve and take a projective measurement, and then we find the particle sometimes left, sometimes right. But again, the magic is, before we take this picture, the particle is really described by this wave function up here, right? It's really delocalized over a lot of sides, very coherently. How do we know? Well, if you look closely here, this is actually a tilted lattice. If we continue the time evolution, we would get a Bloch oscillation, a real space Bloch oscillation. And you can easily calculate that the wave function you would expect to spread out and then refocus onto just a single side. But this, of course, only happens if the particle is completely coherently delocalized. But in the experiment, you see this works. So the particle is completely delocalized. We can take projective measurements, find it left or right. In reality, it's left and right. And if you continue the time evolution, it focuses back perfectly. Any kind of decoherence, right? Like if you wiggle the face, or if by mistake you do some kind of partial measurement that gives you some information about whether the particle is left or right, that would destroy this cat-like superposition, right? And you would not be able to get back to your original site here. But the fact that we do shows you just how coherent these atoms are in these optical lattices. But then it's not only this a single atom. We can have many atoms in this lattice, and they interact with one another. That is given by this second part here. But the nice thing is this interaction is again clean. So if two particles are on the same side, you just raise the energy by a little bit. Anyway, this is realizing this model very cleanly. Additional terms are on the 1% level, right? Again, two spin states of fermions. That also means we're only in one band here, right? So that means at most you can have two particles per side, one spin up and one spin down. Yeah. Okay, so what is the ground state of this model? Oops, what's happening here? What's the phase diagram of this model? What's the ground state of this model? Believe it or not, nobody really knows. This is the simplest model, but it's deceivingly simple, despite the decades of heroic effort, there are many, many open questions, even linked to this model on a simple square lattice. And once you go to different lattice structures, different bends, different interactions or so, things become even less understood. But the cool thing is, it is believed that the phase diagram pretty much, or that it looks very similar to the kind of phase diagram that you find in high temperature superconductors, right? So these materials, these exotic materials that have been discovered in the 80s and can conduct electricity at surprisingly high transition temperature. So this is a phase diagram as a function of temperature and doping, meaning here you have, sorry, I'll get that to that later. So, okay, so what happens? Like, how can I understand this Hubbard model? What happens at high temperature? At high temperature, I have a metal, right? The atoms can just move around fairly freely. And if I lower the temperature, at some point, this interaction becomes important, and that means that I get density ordering. Having 2 particles per side becomes energetically costly, so at half filling, I would have a Mott insulator, 1 particle per side. But the spins are random. Okay? If I get to even colder temperatures, the spins actually start to order. It's not totally obvious why at first if you look at this model, right? Because there is no term describing spin-spin interaction. But if the neighboring spins want to be anti-aligned, they want to look singlet-like. The reason is, if neighboring spins are anti-aligned, they can virtually go on top of each other. As opposed to if they're in the same spin state, right, then going on top of each other is completely forbidden because of Pauli exclusion. So there's a tendency, even without an explicit such term, for neighboring atoms to be anti-ferromagnetic, right? And that means if you lower temperature, we get this kind of super exchange leads to an anti-ferromagnet, to anti-ferromagnetic order at half filling. In the experiment a number of years back, we were able to see this kind of like Mott insulating physics and anti-ferromagnetic physics, and in fact many groups have explored this kind of physics here. Right, and so let me explain this phase diagram now. So this is this axis is temperature, this axis is doping. What does this mean? So here we have half filling, the Mott insulator with where the ground state is the antiferromagnet. But you can then also put in additional charge carriers, either holes or extra particles, right? And if you do that, then you get doping. And what you expect here is a deviated superconducting phase and a charge density wave, but it's actually not clear. For example, it's not clear what wins in this phase diagram, like stripes or deviated superconductivity. It's also not known if there's any deviated superconductivity at all, or whether you need additional ingredients such as a slightly varied geometry, like a diagonal tunneling, as you have in real high TC materials or other ingredients. But in principle, right, this could be explored with these kind of quantum simulation, because we now have a clean realization of this simplified Hubbard model that may or may not be a minimal model for high TC. We have that in the lab. The problem, however, are these little 2 lines here. All of these temperatures were still quite high, right? This is 0.5 T, 1 T, even 2 T. Nevertheless, there was some really exciting physics studied, for example, strange metal physics up here. But we need to get colder, more like 0.05 T, 0.1 T or so, to really get into these interesting regimes. Before I show you how we get colder, let me show you a little bit about the flavor of physics that emerges in this model. Because again, right, it's really surprising how can a model so simple with fairly simple phases like an antiferromagnet, how can that give rise to so interesting questions and rich physics? What's really happening here is that there's a very intricate interplay between the spin and charge degrees of freedom. And physicists since a long time are actually trying to come up with some kind of effective models to try to understand this physics. And I will show you one example that was proposed actually not too long ago. And that also shows you the kind of hope that I have for quantum simulation, that we can actually test these kind of, like hopefully eventually there will be some kind of intuitive understanding of what high TC is, for example, right? Anyway, one of these models, for example, starts with an antiferromagnet. This is kind of like a comic version where you just have Néel order. The real Heisenberg antiferromagnet is much more complicated. But anyway, if you now have a hole in here, you can imagine if this hole wants to move here, it actually leaves behind a string of spins in the wrong spin state, right? So that can't be good. In fact, that costs energy, and that means the hole can't get very far. You get a polaron, kind of, and the hole is actually delocalized over all the different ways it can move, and it's also disrupting this magnetic order in all of those different ways it can move, all in the quantum superposition of all those possibilities, right? And so this really competing kind of like the motion of holes and magnetic order are competing, but maybe you can view this as, or maybe you can come up with some kind of, maybe you can cook up an effective model to understand this. For example, in this case, maybe this is kind of like a string, like the row of atoms in the wrong spin state may form a string. This original missing spin is a spinon, and this charge is a holon connected to the string. Maybe you can cook up some kind of high energy like theory of these mesons, because if you make the string long enough, it could break, like deconfinement. Then you have a string spin, spin that's a magnon, and a new string spin, spinon string holon object. And maybe you have a gas of these kind of quasi-particles, and maybe these strings, maybe they somehow attract each other or so. So it's not clear. It seems like it's not exactly like this, but in the experiments, we have seen nice evidence of these kind of string-like objects. If you just take a lot of pictures, and this was at higher temperatures than we currently have, if we take a lot of pictures and we look for these kind of string-like defects, we can, it seems like we find them statistically significantly, and they behave according to what a theory that's possible to do at these higher temperatures, what they would predict. Good. So yeah, this intricate interplay between spin and charge is really, so somehow the magnetism and the charge movement is really intricately related. But the interesting thing is, it's even like fairly fundamental questions are unanswered. Is the magnetism competing with the superconductivity, or is it the carrier of the Cooper pair? Like, is it causing the Cooper pairs to exist, for example? These are questions that are not currently understood, even for the Hubbard model. Okay, so how do we get colder? The coldest temperatures were at a temperature of about 0.25 T, and many of the experiments I showed you earlier were even significantly higher. The problem is that is pretty hot. This is like a superconductor that's still in the oven, between 600 Kelvin and maybe, in some experiments were even at like a few thousand Kelvin, right? We need to get colder. We need to get to below room temperature and to cryogenic temperatures, right? So how can we do that? And actually, people tried for quite a while. Many people were already kind of pessimistic about this ever working. But what we also had since a while already were bent insulators that are quite cold. The trick is, so one trick we are building this on is the following. if the simplest state I can create in the Fermi-Hubbard model is band insulator. One spin up and one spin down atom per site, right? Excitations from that cost a lot of energy. So if I couple that to a metal, then you would expect that the entropy goes all to the metal, because it's much cheaper to have entropy in the metal than it is to have entropy in the gapped band insulator state. And that in fact works very nicely. We get pretty much perfect band insulators of about this size with exactly 2 particles, like singlets of spin up and spin downs on every lattice site. The difficulty was, how do I now turn this into an interesting state? Right? There were proposals and also some prior attempts to kind of turn this into a half-filled state, right, where I have the Mott insulator and the Heisenberg magnet. And the idea is to essentially double the number of lattice sites. And to do that, we built a special lattice where we can literally double the number of lattice sites by turning each of the lattice sites into a double well. Okay, it's a fairly complicated setup of interfering laser beams. I don't want to go into details right now, but essentially what we can do is every single lattice site can turn into a double well like this. And then I turn this kind of like boring one spin up, one spin down singlet on a lattice site into a singlet on a double well, right? Up, down, minus down, up in each double well. And then I can combine these double wells to each other, right? And maybe that could be a good route to get to a low entropy magnet at half filling. So we built this, we tried this in the experiment, and in the end we end up with this kind of equal tunneling strength and double the site. And what we find is this. So this is a correlation plot of spin-spin correlations. Well, you don't have a comparison, but they look very good. We get a very nice Heisenberg-like antiferromagnet. How good is it? Well, here's the correlation strength of the antiferromagnetic correlation as a function of bond distance. The previous work is represented by this red line. This was the previous best temperature of 0.25 temperature. Actually, luckily, at half filling, things can be computed. The sign problem only emerges as you dope away from half filling. It makes sense that half filling is just a spin system. Only away from half filling do you get these intricate interplays between spin and charge. Anyway, so what we find is, if you compare to these computations, we have pretty much saturated, yes, we are much colder, and we have pretty much saturated the antiferromagnetic order. Our system looks like a pretty much perfect Heisenberg antiferromagnet. The points like somewhere in between 0.1 and 0 T were tunneling. And if you fit this, we get that the temperature is 0.05 plus minus 0.05. But I mean, it's saturated, right? It just means we are very close to zero temperature on this with regard to spin ordering. Which is remarkable if you think about it, because the spin ordering is already a higher order effect, right? Like the Hamiltonian has no spin-spin interaction. The super exchange is already kind of a higher order effect, but not high order, but not as high order as, of course, the spin and charge interaction. Good. So we were very happy, but then the big question was, how do we get into the doped regime, right? Because that's where really the interesting physics is. And to be totally honest, I was actually slightly worried about that, slightly pessimistic maybe even, because see, like I can see how I can make a nice Heisenberg magnet in this regime where it can be computed, but that also means that like it's not as complex of a quantum state. And if I now bring in holes, well, how do I now bring in holes in a way that they really find their kind of like close to ground state, like weave them in the correct kind of quantum mechanical way? Maybe that is very difficult, right? But then my students, the nice thing is once you have a quantum simulator, you can play with it. You can try things out. You can just, play Lego with it and see what happens. And they tried a bunch of different things. And one thing that I found works really well is instead of directly going to double wells and creating this Heisenberg magnet, you can just reduce your lattice depth by a lot. And that means the particles become weakly interacting, and we get a Fermi sea in this lattice, kind of, but still starting from this really low entropy band insulator. And if we keep the band insulator well isolated from this metallic halo that has absorbed the entropy, or we can even eject those atoms, then we can get quite cold, even in a doped regime, by first unloading the lattice and then reloading it again, kind of in within a different volume. And that way we can change tuning. And so when we did this, this is again the antiferromagnetic correlation as a function of distance. The more you dope via holes, right? Of course, the whole movement is counteracting the antiferromagnetism. You see how this goes down. But the good news is, well, okay, now we don't have reliable theory necessarily to measure our temperature. The best, what's often considered the best kind of theory are these CP-AFQMC calculations. The Flatiron Institute has done an effort to really try to benchmark different theoretical methods and kind of present what they believe is the best kind of approximate theory. This is not unbiased anymore, like quantum Monte Carlo. You have to put in trial wave functions, and results do depend on what trial wave functions you put in. But interestingly, yes, our nearest neighbor correlator, they look very nicely close to very cold temperatures in this AFQMC simulation, right? But then we got the first surprise. If you look at longer distance correlations, we actually find more antiferromagnetism than AFQMC would ever predict. Okay? So what's going on here? Is our experiment not exactly the Hubbard model, or is there something wrong? So we looked a lot into all kind of aspects of it. Yes, we're actually having the amount of doping we think, and yes, the imaging is trustworthy, the interaction is measured correctly, and so on. But also the terms beyond the simple Hubbard model are kind of like only a % level deviation that can't really explain this. So we're kind of suspicious that this may actually be a problem with the theory, because the nearest neighbor correlator, they agree very nicely, which makes sense since in the theory, the nearest neighbor terms are what determine most of the kinetic energy. The longer distance physics, right, is much more fragile and may depend more on trial wave functions. So I don't know, but all I can say is there we find interesting deviations. Also, we have started to comparing this with other methods. We do find some nice agreement. Here's a paper by Evgeny Kozek, which is still being reviewed, which finds nice agreement with our data. But the Flatiron people think there's something wrong with this. Anyway, at higher temperatures, where you can still do quantum Monte Carlo, so Devereux at Stanford, they really push kind of the Monte Carlo to the extreme limit. This is at significantly higher temperature, but we can also go to that temperature, and there we find very nice agreement with their quantum Monte Carlo, and our experiment agrees better with their quantum Monte Carlo than the Flatiron theory. So maybe we are really benchmarking state-of-the-art numerics here, right? Okay. But it's not just about quantitative comparisons and benchmarking of theory. So what happens? Can we see any kind of new interesting effects, new physics? Or just in general, can we study any of the kind of physics that you expect in the Hubbard model at low temperatures, like pseudogap physics, stripes, and so on? So the first thing we noticed is that, we can use optical potentials that we project to shape our potential landscape, to flatten it a bit. There's a little bit of disorder present, and we can compensate that disorder using this projection system. The first thing we notice is that at around 10% doping, we were never able to quite eliminate our disorder. And that made us suspicious. So what does that mean? Is maybe the compressibility doing interesting things there? And so we went ahead and intentionally created a potential step in an otherwise flat potential landscape and measured the density of the particles across this potential step. And that allows us to measure the compressibility directly, right? Like, how does the density react to a step in the chemical potential? And when we do this, well, first of all, at high temperatures, where you can still do numerics, we have a nice comparison to DQMC, and that seems quite reasonable. But interestingly, if you now go to cold temperatures and take that same measurement, things look much more interesting. We actually find a peak in the compressibility here at around 10% doping or 8% doping. This is, by the way, the kind of doping regime where in high TC you find the highest transition temperatures. So this is interesting, right? Here, for strong doping, the compressibility is the same, independent of temperature. Here, at cold temperatures, we get twice the amount of compressibility compared to higher temperatures. So that's quite significant, right? So what's happening here? I mean, one possibility is that we may be able to view this kind of like a Widom line, like meaning there may be a phase transition below, right? Often these thermodynamic quantities, they do depend on, if you have a phase transition, then it affects the thermodynamic above. Like, for example, even ice-water transition, even at much higher temperatures, you see some anomalies because of that transition. And so maybe this peak is just separating a pseudogap from a metallic region, like a pseudogap phase and a metallic region. So what's a pseudogap phase, right? This famously has been, this is seen in all the high TC and all the Hubbard materials, right? The idea is that, let me show you this. In all these Hubbard materials, you find very weird behavior even above high TC, above the critical temperature to D-wave superconductivity. In some ways, it looks like a metal, but in other ways, it doesn't look like a metal at all. It does not behave like a Landau kind of a metal. For example, if you look at the Fermi surface here via RPAS in condensed matter experiments, you find that in certain directions there is none. Right? What does that mean? Like normally metal always has a closed Fermi surface. Instead, you find these Fermi arcs, and there are many questions on how these Fermi arcs are linked to the high TC kind of physics. What this means is that there are no good quasi-particles here in this kind of very unconventional metal at these antinodes here at these points. Okay. Now, but the pseudogap is not just some kind of strange, some kind of weird metal. It's also what is believed, like what the high temperature superconductivity grows out of, essentially. So this is what turns into the D-wave superconductor, it is believed, right? But it's not understood what it actually is. And over the last decades, there were endless discussions about what it could be, and there are many open questions. Okay, so how can we see if we have maybe a pseudogap state there, and how can we analyze it? In condensed matter physics, as I showed already, RPAS is a nice way, but in general, there are many different spectroscopic techniques, and the verb pseudogap is also derived from that, because you see a strong suppression of spectral weight at low frequencies, kind of like a gap-like feature without it being a fully gapped state, right? So what can we do with, can we do any kind of spectroscopy in cold atoms that particularly probe these antinodal regions here, or that are particularly sensitive here, right? So it's actually nice. We can do something very similar to Raman spectroscopy with the cold atoms just by periodically modulating our tunneling, right? Like the atoms can tunnel X, they can tunnel Y. Now we can modulate that tunneling periodically at some frequency, and that then corresponds to an excitation at a certain energy. But we have a choice. We can do it in phase, the modulation, or we can do it out of phase. And this exactly corresponds to the A1 and the B1 response in Raman transition in condensed matter physics, if you're familiar with that. In particular, the B1 is interesting because here I've plotted the structure factor, kind of like what part of the Brillouin zone are these is the spectroscopy probing. It is really these antinodal regions if you look at the B1 Raman response. And in the experiment, what we do is we prepare the state, then we kind of shake the tunneling, and then we actually go back all the way to the band insulator, because there we can very nicely probe whether we have created an excitation or how many excitations we have created. And so what we are then measuring is kind of like the energy absorption that then creates entropy in the system that then is converted into holes in the band insulator. So what did we find? Well, first of all, at low frequencies, at strong dopings here, right? This is as a function of doping. This is strongly doped where you expect a metal, still kind of weird metal, but essentially a metallic phase. And what we find is a Drude-like peak, meaning that the frequency falls off, the modulation response falls off with frequency, kind of like a Drude-like peak. In the A1 response, if we now change the doping, maybe something interesting happens, but no drastic change. In the B1 response, however, we get a very interesting picture here. You see a very distinct loss of spectral weight for low frequencies here, right? And this looks a lot like a pseudogap. And in fact, this is happening exactly where we find the compressibility maximum also. Right? So this looks a lot like pseudogap spectra here, for example, ARPAS or Raman spectra in the pseudogap, where you have a strong suppression of spectral weight at low frequencies, which we find at low dopings here. Right? But the nice thing is we can also now look what are these excitations. We can actually sit on one of these peaks, and then we can see how these magnetic, like the magnetic response directly, and how the magnet is being driven here when we apply the modulation. And we see there's no response in density, but there's a strong response in the spin. And so this is consistent exactly with a 2-magnon peak, just like what you have in materials like Hubbard materials in high TC. Right. So yeah, this is very nice evidence for the pseudogap here. One interesting question in condensed matter is, how does it depend on the interaction strength, right? Some people believe you can start with kind of like a weakly interacting system and then extrapolate that and get this pseudogap physics already this way. And others believe, no, it's really qualitatively different. You need you need to be really deep in the strongly correlated regime to even just have this effect at all. Interestingly, if you just measure the peak position here as a function of interaction, we do find that this kind of goes towards zero here at small interaction strength, and that the pseudogap seems to vanish here as we reduce the interaction strength to about 3T, right? And here I've plotted both together, the compressibility maximum, which also disappears down here, and the spectroscopy gap, which both disappear once you get to interaction that is weak enough here. And I think this is kind of interesting to see that it seems to not continue all the way down to to very weak interaction strength. Good. So, yeah, apparently here as a function of interaction strength, we have this kind of pseudogap to battle transition. And as I said earlier, there was the compressibility maximum. But one question is, does this compressibility maximum, one reason how you could imagine a large compressibility to arise is actually if you have stripe physics. So could this be linked to stripes? Is it stripes instead? Or is that just another side of the coin that we're exploring here? So what are stripes? Stripes are kind of a cartoon model of how the system could kind of like arrange itself by kind of phase separating essentially if you have this Heisenberg-like magnet doped with holes, right? Cartoon-like, what you could imagine is if all those holes line up into straight lines, then in between you could have a perfect magnet without any problem, but the domain has flipped across these lines where the holes are, because if you move the holes over by one, all the atoms would tunnel over, so that gives you a kind of a sign flip in this antiferromagnetic order, right? There is a lot of theory of this. The reality looks quite a bit different. Like, it's not this cartoon model. These stripes, if they exist, they would be much more delocalized, soft, wiggly kind of. It wouldn't be this kind of black and white kind of clean picture. In fact, people believe that there's hardly any signature in the charge order, even if you took a snapshot. It's mostly magnetic correlations that would respond to this. But yeah, exactly. Okay, so what do we see experimentally? Well, the first thing is we can study the nematic response. It's a little bit more indirect, but it's actually kind of interesting if you think about it. The question is, if I vary the, and this is a bit different to the Raman response. What if I have my system and I vary the tunneling in the x and in the y direction? I make it. What if the atoms tunnel more in the x direction? That would mean a super exchange is also larger in the x direction, and I would get more magnetic order in the x direction than I get in the y direction. And we can quantify this magnetic order as a function of imbalance between the x and y tunneling. We can fit that, and that is then the nematicity. So how susceptible is the system to breaking this x and y symmetry, right? And if you measure this, the nematicity, so how much does the AFM order respond to this asymmetry in x and y? At high temperature, it agrees nicely with DQMC theory. But if you lower the temperature to our coldest possible temperatures, once again, surprise, surprise, we find kind of a peak at around 10% doping in the nematicity. That could be significant, because what that could mean is you can kind of think about this amount of nematicity as kind of just the background of, I mean, of course, if super exchange is larger in one direction, then you have more magnetic order in this direction. But you could have, but this is a significantly higher nematicity here, beyond what you would expect from just the super exchange. So maybe what is happening there is that this asymmetry kind of creates stripe-like physics, where stripes kind of align with that imbalance in tunneling, and then the magnetic order is particularly non-disrupted in that kind of other direction, and this would show up here as a stronger nematicity. Right. Anyway, so this. We find quite interesting that we do find this peak in the nematicity also around, again, at similar doping levels where we also see the compressibility maximum. So maybe this is stripes. Can we see stripes more directly? So this is work in progress, maybe. One problem is if you do even the best available theories, they predict that these stripe correlations most say that in charge, you don't see any kind of order in charge, and it's mostly that there is some tendency for these domain walls, kind of like where the magnetic order flips sign. We can plot this in the sign corrected. Sorry, I should explain this kind of picture. This is sign corrected, so it's AFM. If it's all red, it means it's an AFM on one sublattice, and if it's all blue, then it's the AFM on the other sublattice. So I flip the sign of every second spin here. Yeah, anyway, if you try this experimentally, we get pictures like this. Interestingly, so it is subtle because here the stripes are not pinned. They could be left, right, fluctuating wildly. But very often we do see data sets where the magnetic order as a function of bond distance flips sign, actually. And so this would be kind of what you would expect for stripes. Again, the problem is the expected signals are quite small. But what's also interesting is that very often we find in the diagonal direction, we find these kind of zones where you have opposite sign in the AFM order, which would make sense if you imagine that stripes are either horizontal or vertical. So it averages out in the X and Y direction, but in the diagonal, the signal wouldn't completely average out. But to get this a bit more controlled, we're actually thinking, can we maybe try to pin the stripes a bit, right? And so what we do is we apply potential modulation. We did some theory here with TCM Ratz, where if you have a potential, if you apply a certain potential stripes like this, then you would expect to pin the stripes. And if you do that, we find indeed that that across these kind of induced stripes, we find clearly that the sign of the AFM order flips if these are strong enough. So in this case, if the amount of corrugation is about 1T or so, which is not terribly strong, we do find that the magnetic domains flip sign across those kind of induced stripe regions. But anyway, this is work in progress. There are also proposals. What should be really interesting is if you add diagonal tunneling. We just started doing that and exploring that. That should also affect this and make the stripes much more robust. But it could also potentially help a lot to get towards a D-wave pairing and D-wave superconductivity. And I mean, we haven't probed anything in that direction. But and then in total, the nicest our new lattice, where we can do all these things, is programmable in all kind of interesting ways. We can make triangular lattice, sleep lattice, honeycomb lattice, and so on. So there are lots and lots of things. Or we're also preparing to do like multi-layer systems and so on. So there is a lot to explore, and we are also having a whole bunch of ideas on how to push the temperatures even more. Good. So. Yeah, so if you just take one thing from this talk, it's kind of like we're taking the superconductors out of the oven and put them maybe not quite at liquid nitrogen temperature yet, but well below room temperature. And so that's the state of the art of this quantum simulation, and it's certainly fun to to get into these regimes where which are highly relevant for quantum matter physics, but where computational methods are really at their limits, and kind of like some kind of real life quantum advantage, where we can build a machine that can do things that even the biggest supercomputers cannot compute. I don't have time to talk about the things, but let me just mention real quick in our other teams. In Rubidium, we have studied some fractional quantum Hall physics. Actually, we're about to put a paper on for like a 3-particle Pfaffian state, we realized. We also looked into anion physics, MBL, and things like that. And in the erbium experiment, there we have a long-range interaction through magnetic dipoles, where we see these dipolar quantum solids. But also, we can study some kind of new quantum optics, where we see super and subradiance in a programmable kind of arrangement of atoms. And that is really fun, because that means that we can have sub and super radiance in a programmable, strongly correlated regime. where you could use it to really build interesting quantum networks, quantum setups, and so on. Good. Yeah, with that, I would like to thank all the team. Actually, a number of these group members have graduated already. I need to update the picture, but they're still involved in some of the physics I showed. And yeah, and we need a postdoc on the lithium experiment I was just telling you about. So if you have interest, let me know. And thanks to all the funding agencies, and thank you very much for your attention.
Okay, thanks, Markus, for fantastic talk, beautiful results. Questions?
That's one there.
Yep, help.
Thanks for the beautiful results on the top. So now that you entered this regime where numerically, verifying or testing is kind of not that straightforward, is there a way to experimentally benchmark? For example, in the past, we've done these mini-body HOM interference type experiments in the bosonic system to measure the purity of the state. Could you think about some mechanism with which you benchmark just based on the purity of the experiments alone, using maybe some similar?
So, in principle, these HRM homomundal mini-body interference could, in principle, be extended to these systems, albeit in a bit smaller system, I would say, like for smaller system sizes. This could be realistic. Other things we do is we go back to a band insulator and see how much entropy, like how reversible we were. I'm saying reversible, not adiabatic, because of course it could also be that one ends up in some kind of metastable state sometimes, right? So and still be able to go back. I think it's unlikely, but it's not a proof that we're not doing that, right? So yeah, that's a very interesting question, right? I mean, I also, one thing that will help already if there are multiple experiments now getting into this regime, and we can challenge each other, and things need to agree in order to be trustworthy, right? And or other things are you can kind of engineer some kind of reservoirs that's coupled to like a bath or so. Then you can exclude certain types of metastable that you haven't actually made it to the ground state, or so maybe. No, but that's life. I mean, and there are certain pockets you can compute, and there are certain finite size kind of computations where you can directly compare it, right? Like ED or a DMRG or so. That's only small, but we could at least try to do exactly those smaller systems, and then maybe trust if you double and double and double the size that it behaves similarly, right?
Is your doping a coherent process, or is it an incoherent process? Your doping.
Oh, that's totally coherent. But that was my point. If you just had an undoped system, so we can do different things. We do go back to the Fermi sea and then ramp it up, and so that means yes, it's very much coherent, right? Just adiabatically going into the right. So yes, the holes are quantum mechanically delocalized and so on. We can also do other things. We have done it with one hole that we just place into an undoped magnet and then see how it moves. And there we found some interesting polaron movement. We could do it with two holes, right? Imagine placing two holes at particular positions and see if those two holes would now move in a correlated fashion or independent of one another, right? If they move in a correlated fashion, maybe that's a nice way to see a D-wave Cooper pair, just one, right? I don't know. These are all things on our bucket list.
Mike.
To what degree are you able to model long-range Coulomb interactions? So
in this system, we don't, right? I mean, it's pure on-site interaction. We do have another experiment where we have magnetic dipole-dipole interaction, and for example, if you align the dipoles like this, then there's some kind of longish range. Interaction, maybe not as long range as Coulomb, but certainly as long range as shielded Coulomb, which is the more relevant one maybe. But I must say, we're not quite at those temperatures with those systems yet. So we'll have to see if we would be able to get as cold there. But in principle, there are also many people working with molecules, and once that's really working, you may be able to do that with electric dipole-dipole interaction. But that's not in principle possible, but not on this exact machine, and it could also be that it's generally quite difficult. How to measure the temperature in the doped system, you say? Well, no. The best, we pretty much only have this AFQMC to compare to or that collaboration, for example, has already tried to compare different theory methods. That gives us a certain amount for the nearest neighbor agrees with us, and and would suggest that we are at similar temperatures, like 0.05 T over T or 0.1, maybe closer to 0.1 T or so. But that relies on their theory. So no, we don't have a direct way to do it. You could imagine other ways of. So yes, thermometry is an interesting question for the future, right? You could think about coupling two systems. And then maybe one is easier to do thermometry on because you know how to compute it, for example, or finding some observables that give you a more direct link to thermometry. But luckily, I mean, even with these uncertainties, the nice thing is we see all this qualitative physics now. But for temperature, we currently rely on these computations.
Okay, maybe one last question. Go ahead.
Wondering if there are sort of theoretical or experimental predictions on multi-body correlations, like 3 or 4.
Good. On what?
3 or 4 body correlations. Systems.
Yeah. No, right. I mean, so the nice thing is that we can not only measure population and spin order, but also higher order correlation. For example, one thing we did before we did these experiments, it's still a bit higher temperature actually, we hadn't implemented the cooling yet, is to measure higher order correlation functions to see Nagaoka ferromagnetism. So there what we did is we say, okay, let's look at a position where we find a hole and look what the magnetism is doing around that. Right, and we found that at the hole, like in the vicinity of the hole, we had positive correlations, meaning there was. So we were able to identify ferromagnetic bubbles essentially around the holes. So this Nagaoka ferromagnetism is a famous example where the motion of particle actually leads to magnetism rather than inhibiting it in a frustrated triangle, the lattice. So that's an example. We can totally measure these higher order correlations. We could also, the one kind of thing we really want to also implement is do additional steps before you take the projective measurement, right? Normally projective measurement, it just projects on every lattice sides the population, but we may want to measure coherences, right? So that means you could apply some kind of like gate-like sequence and then do a projective measurement. And that way you could really distill interesting you could look for the presence of interesting wave functions, kind of, and distill that and get a more direct. There are interesting proposals on how to directly look at D-wave wave functions that way. So we're preparing to have more tools to do that.
All right. With that, let's thank Markus for a wonderful talk.